In part 2 of vectors in 3 dimensions, we can also perform the dot product on vectors in 3 dimensions by doing the same thing we did in 2 dimensions. The only difference is we're going to have a z component. Remember, a dot product gives you a scalar quantity, not a vector. So in problem 5a, when I find the dot product of negative 1, 2, 3, 6, 5, negative 1, I'm going to multiply negative 1 times 6, add that to 2 times 5, and add that to 3 times negative 1. So negative 6 plus 10 plus negative 3 is going to equal 1. If I do the same thing with my vectors in ijk form, just remember that the i's go together, so you're going to multiply 2 times negative 1, plus the j's go together, plus the k's go together. So you get negative 2 plus negative 6 plus negative 8, which is going to be negative 16. If you have two vectors on a coordinate plane, this formula here is the one we use to find the degree of the angle between them. We did the dot product of the two vectors and divided by the product of the magnitudes. It works exactly the same way in 3 dimensions. We also found out that if the dot product of two vectors was 0, then the two vectors had to be perpendicular or orthogonal. So in example 6, I want to show that vector u is orthogonal to the second vector 5i minus 4j plus 2k. So when I do their dot product, it better equal 0. So I'm going to do 2 times 5 plus 2 times negative 4 plus negative 1 times 2. So 10 plus negative 8 plus negative 2 is 0. Therefore, the two vectors must be orthogonal. The direction angles of a vector. When you draw a vector in the 3-dimensional coordinate plane, you have an angle between that vector and each of the axes. These are called direction vectors, and we're going to use the Greek letters alpha, beta, and gamma instead of theta for these 3 particular angles. So if you want to find the angle that your vector makes with the x-axis, we would do whatever a1 is, the I component, and divide that by the magnitude of the vector. If we want to find the vector's angle with the y-axis, we would take a2, the j component, and divide it by the magnitude. And if we want to find the angle between the vector and the positive z-axis, we would take a3, the k component, and divide it by the magnitude. So in this problem, I want to find the direction angles of the vector ai plus 2j plus 3k. So first, I'm going to do cosine alpha is equal to a1 is 1, and I'm going to divide that by the magnitude of the vector. So the magnitude is 1 squared plus 2 squared plus 3 squared, and I take the square root. So I get the square root of 1 plus 4 plus 9, which is the square root of 14. In order to find alpha, you have to take the inverse cosine of 1 over the square root of 14. And you should get approximately 74 degrees. To find the direction vector with the y-axis, we're going to do a2 divided by the magnitude. And since I've already found the magnitude, I just plug it in. The inverse cosine of 2 over the square root of 14 is approximately 58 degrees. And to find the direction of the vector with the z-axis, we're going to do 3 divided by the square root of 14. Take the inverse cosine of 3 over the square root of 14, and you should get approximately 37 degrees. Remember that those are the measure of the angle with the positive x, y, and x, y, and z axes. If you know the magnitude of a vector and you know the 3 direction angles, you can write the vector form by doing the magnitude times the cosine of alpha, the magnitude times the cosine of beta, and the magnitude times the cosine of gamma. The last formula that we're going to work with is that if you square the cosine of alpha, square the cosine of beta, square the cosine of gamma, those three quantities end up equaling 1, which is a good thing to know when you're trying to do this. A vector makes an angle alpha pi over 3 with the positive x-axis and an angle beta 3 pi over 4 with the positive y-axis. We want to find the angle gamma that the vector makes with the positive z-axis, given that gamma is an obtuse angle. So I'm going to start by finding the cosine of pi over 3 and squaring it. I'm going to find the cosine of 3 pi over 4 and squaring it. I don't know gamma, so I'm going to leave that alone because that's what I'm going to solve for. Well, we know the cosine of pi over 3. The cosine of pi over 3 is 1/2. The cosine of 3 pi over 4, because that's in the second quadrant, is negative square root of 2 over 2. Now I'm going to square those and add them. So I get 1/4 plus, this becomes 1/2. One-fourth plus 1/2 is 3/4. I'm going to subtract 3/4, and I get 1/4. I have to square root this, and I get the square root, or I get the square root of 1/4 is 1/2. So now when I do the inverse cosine of 1/2, I'm going to find out that the answer is 60 degrees, or pi over 3. But the thing is, we just said that this is an obtuse angle. So if it's an obtuse angle, pi over 3 is not an obtuse angle. That's an acute angle. So another answer we could get that gives us positive, I guess I should have done this, which was plus or minus. So if you do the inverse cosine of positive 1/2, you find out the answers are pi over 3 and 5 pi over 3. If you do the inverse cosine of negative 1/2, you're going to get 2 pi over 3, and you're going to get 4 pi over 3. Well, these two angles are outside of the 0 to 180 degree range that we normally work with when we're working in coordinate plane. So if I want to pick the obtuse angle, I'm going to pick that one. And that is the end of Vectors in 3 Dimensions, Part 2.